Hello there, welcome to our new unit. This unit is going to be about the Pythagorean Theorem. Just have a quick little warm-up here with some fractions. So I'm going to have you take a second, go ahead, work through those 4 problems, and pause the video while you do that, and then when you come back I'll have answers up here for you. Alright, there you go. Go ahead, check your answers. You are welcome to leave these improper here as long as they are simplified. Alright, so today's lesson is a little introduction to the Pythagorean Theorem. There's a little paragraph here about the Pythagorean Theorem and how it originates. Basically, it is invented essentially by the man named Pythagoras. He was a mathematician in ancient Greece, and he used the relationships between the sides of the right triangle. He was able to develop kind of this theory about what exactly happened with the sides of the right triangle. It wasn't until later on in the 16, 17, 1800s that they started to put variables with math. So the variables became a part of things later on then. But for right now, as we talk about the right triangle, there's a couple parts that we need to know. These 2 sides that make up the right angle are called the legs. And the way that I remember that, I'm going to use some color here, they form an L. So the L make up the legs here. And this side over here, the longest side of the right triangle, is actually called the hypotenuse. The hypotenuse can always be found because if you start at the right angle and go straight across the right triangle, you'll be able to find the hypotenuse then. It's the longest side because it's actually across from the largest angle inside the triangle. So things special about the hypotenuse, it is the longest side, and it's located across from the right angle. So no matter what orientation our triangle has, even if we saw one this way, we'd still be able to find the hypotenuse by going across from the right angle. So we're going to actually see that in some of our problems. If you flip over to the next page, Pythagoras was able to identify that in the right triangle, if you squared a leg and you summed them, that was actually equal to the square of the hypotenuse then. So he put it into words like that, and then we put the A, B, and the C with it. A and B are always going to represent the length of the legs, and C is always going to represent the length of your hypotenuse. So we can interchange A and B because of the commutative property of addition. So you can basically pick whichever one is which, and I'll kind of switch back and forth during our notes today. C will always be the hypotenuse though, and notice C is over by itself. So if I'm looking at example number 1, this is a right triangle here. We have 3 and 4. Let's just call this A and call this B. Here's C, and I know it's C because it's across from the right angle. So first thing I'm going to do is write down the formula. A squared plus B squared equals C squared. And now I actually substitute in place of A, I put a 3. So I have 3 squared plus, in place of B, I put a 4 squared, equals C squared. Go ahead and actually simplify here. So 3 squared is 9, 4 squared is 16. And we can go ahead and actually combine our like terms. So 25 equals C squared. Only problem, if you remember, we don't want C squared, so we have to find out a way to actually undo squaring. And if you kind of think back to our first chapter, we said square roots and squaring actually undo each other. So what we can do is take the square root of both sides. I have to do it to both sides because this is an equation, so I have to balance it out. So the square root of C squared is just going to give me C because those operations essentially undo each other. And the square root of 25, if we think back, 5 times 5 gave us 25. So that C value, the hypotenuse, is 5 centimeters in this triangle. If I take a look here, this is just a straight up example. A is 6, B is 8. So A squared plus B squared equals C squared. That should be a lowercase b. 6 squared plus 8 squared equals C squared. 6 squared is 36. 8 squared is 64, equals C squared. 100 equals C squared. Square root, 10 equals C. In this one, 10 squared plus 24 squared equals C squared. So if we have 10 squared, that's going to give us 100, plus 24 squared is 576. and that's going to equal c squared. So it's going to be 676 equals c squared. Take the square root, and I'm going to get that 26 equals c. Now you've probably noticed so far that all of these have worked out to be really nice numbers. That's because they are actually called Pythagorean triples. And Pythagorean triples are sets of whole numbers that actually work out. Obviously, we can't include integers because they're lengths, so they're not going to be negative. These are kind of the basic Pythagorean triples, 3, 4, 5s, 5, 12, 13s. We'll typically see those on a regular basis, and what you'll also see is you will actually have multiples of them. So I could have a 3, 4, 5, or I could double it and I could have a 6, 8, 10. That's a very common one. You could triple it. You could have a 9, 12, 15. Those are all possible. 5, 12, 13 is another really common one that we see, but then this is a list of a lot of other ones that have just going up to 37 being the smallest side. So there are infinitely more of these as well because all of the multiples of these too. In here, word problem, how can you, well, this one is just how can I determine if a triangle is a right triangle? So what you can actually do to take care of this is to take the formula, and if I'm given 3 sides, C would have to be the hypotenuse, which we know is the longest. So in a triangle with sides 4, 5, and 9, the longest would have to be C. These other two would be interchangeable as A and B. So a squared plus b squared equals c squared. So I'm going to plug in 4 squared plus 5 squared equals 9 squared. And I don't know if this is true, so I'm going to go ahead and put a question mark over top. 4 squared is 16 plus 25 equals 81. We don't know. 16 plus 25, if I go ahead and put those together, that's going to give me 41 equals 81. That's a no-go. So this is not a right triangle because it does not fit into the Pythagorean theorem. So the Pythagorean theorem works both ways. It lets you solve for sides if it is a right triangle, but it also lets you check to see if something is a right triangle as well. In this picture, if we had to pick which one would be the hypotenuse, hopefully you're looking and saying 10 because that's the longest. So let's just call this A and B. So a squared plus b squared equals c squared. 8 squared plus 6 squared equals 10 squared. We don't know. So this is 64 plus 36 equals 100. And 100 equals 100. So that is true. So we can say yes, it's a right triangle. Word problem 1, the legs of a right triangle are equal. Given the length of the legs, find the length of the hypotenuse. Legs are 5 centimeters. I like to just draw a picture. The legs make up the right angle. This is the hypotenuse across. So 5 squared plus 5 squared equals c squared. So 25 plus 25 equals c squared. Take the square root of both sides. And c is going to be equal to the square root of 50. We know this is going to be about 7.1, but we can actually go ahead and check on our calculator. So the square root of 50, and we get 7.07, so we can just say 7.1 centimeters. That squiggly equal sign tells me about, so it also lets me know that I've rounded. And we'll pick up with word problem 2 for tomorrow's lesson.